In this video, we consider a linear time invariant system with impulse response of h of t and a white noise. And we want to characterize the relationship or the correlation or the behavior of the joint behavior of input and output. The importance of this video is not just because of response of LTI, deterministic LTI system to white noise, but more importantly because in next chapters we want to be able to characterize any arbitrary random process y of t as a combination of a simple linear time invariant system, which could be described by a small number of parameters and a white noise. These could help you to compress your audio or video signals and or also better characterize many random processes. So particularly here we consider a linear time invariant system and a white noise. So assume that your LTI system is characterized by a unit impulse response h of t, and the input be a white noise with autocorrelation function Rx of t1, t2, and this by definition is mean of x at time t1. So this x taken at this sample and then x at time t2. If is a complex random process, remember to put conjugate on the top of second here. So we call it a white noise if this autocorrelation function is a delta of t1 minus t2 times qt1. Qt1 is called the instantaneous power of the random process at time t1. This being white means that any two sample of your random process at time t1 and at time t2, if time t1 is not equal to time t2, these sample xt1 and xt2, their cross correlation is 0. That means that they are orthogonal. So obviously we could, from the previous videos, if you want to calculate the cross correlation between x at time t1 and y, the second one at time t2, which is equal to mean of x of t1 and then y at time t2, this we have shown that this is equal to rxx at time t1 and t2 convolved with h of t2 conjugate, if you put if you assume that this is complex. If not, so and then this is rx x of t1 t2. So now if you do convolve a delta function with this guy, obviously this delta is substituted by that, so this will become equal to h of t1 minus t2 times that. So you could quickly simplify this one, because you know that delta of t convolved with any signal, any x of t is equal to x of t. So it's just replaced. But here you have a time delay of t1 in there. And remember that delta of, let's say, a is always equal to delta of minus a. So it's just a time delay there. Now, if you want to get y of, let's say, t1 and t2, we have shown that this is equal to rxx of rxy of t1 and t2, which is convolved with h of t1. Okay, so I need to convolve this guy with h of t1 in order to get ryy. So ryy, I get this one convolved with h of t1, and then I get, so if I convolve this with h of, or you could say that you convolve this guy with h of t2 conjugate and also convolve it with h of t1, and then you get this one. So if you simplify that, you get this one. So the autocorrelation function of the output yt1 and t2 is just this convolution of h of t1, and obviously this could be simplified a bit by changing the dummy variables a little bit.